Hi, all you cool cats and kittens. Today we're going to graph quadratic functions. And we are going to start with our parent quadratic function. So parent is the basic shape that we should understand before we change that shape in any way. So our parent function is simply y equals x squared. And a great way to come up with a graph is to construct a table of values, and that's what we have here to the left. These are some x values that we can plug in. That will give us some y values that we can plot. Negative 3 squared is positive 9, negative 2 is 4, negative 1 is 1, 0 squared is 0, and then we go back up. So as we go to plot those points, negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, 3, 9. You'll notice that the points sort of repeat on either side, and we should connect them with a smooth curve. And the shape of a quadratic graph is what we end up calling a parabola, and that's that U shape. So we are not graphing straight lines anymore. We're actually going to graph a curve because now we're dealing with x squared. And as we graph our quadratic functions, we're going to see that we can write them in 3 different ways, and each of these different ways gives us some different information about what that U shape is going to look like. We have standard form, where there are no parentheses, ax squared plus bx plus c. In vertex form, we have a set of parentheses where we see a square, and there's an h and a k that we're going to pay attention to, and that tells us the vertex of the graph. And the third form we're going to look at is intercept form, where we have a P and a Q standing in for numbers, and those are going to tell us our x-intercepts. So from each of these different forms, we get different information. But before we look at that information, we should understand some basic things about our quadratic graph. So the shape of a quadratic graph, as we discussed on the last slide, is a parabola. And it is a parabola because the degree of a quadratic is degree 2, x squared instead of just x from our last unit on lines. The end behavior of a parabola is that both ends either go to positive infinity if we are drawing a U shape that opens up, or both ends will go to negative infinity if it's a U shape that opens down. The turning points, there will only be one, and that turning point will be what we call the vertex. Now, on the parent graph, that one we just graphed, the most basic parabola, the vertex is always at the origin. So that point 0, 0. When the vertex is the lowest point on the parabola, when we are graphing this U shape, then the vertex is a minimum. It's the lowest point in the valley. If our graph opens the other way, our parabola opens down, then it's the highest point on the mountain, and the vertex is a maximum. So this, again, is our parent function, and our vertex is 0, 0. You might have noticed on that graph we just drew that there were lines on the points, on the left and right that kind of were mirror images. And that's because each parabola has an axis of symmetry. That's the line that cuts the graph in half and creates a mirror image. So for our parent function, it is symmetric about the y-axis, and that's the line x equals 0. So that would be our mirror image for the parent function. When we are dealing with a parabola, the good news is the domain is all real numbers, which you could also write as negative infinity to positive infinity. The range of our original function is y greater than or equal to 0, or 0 to positive infinity. On the parent function, we have an increasing interval from 0 to positive infinity and a decreasing interval from negative infinity to 0. So this is all for the parent function. Those can change depending on what our graph actually looks like. When we go to graph, we're going to pay special attention to the x-intercepts. And there are 3 possibilities for our x-intercepts. If there are 2 zeros, that means there are 2 x-intercepts, and they are both real. If there is 1 0, we call that a bounce 0. That means that the vertex is the x-intercept, and we count this root as double, counts twice because it's x squared. If we see a graph with no zeros, that means our graph doesn't cross the x-axis. And that means we have 2 imaginary roots. Now, we used several different words there to describe our x-intercepts. So when I think about a quadratic or a polynomial, I always think that solving it rocks. And these letters in the word rocks help you remember that these 4 things are all the same. So the R stands for roots. Roots can also be described as zeros. Zeros can also be described as x-intercepts, and x-intercepts can also be described as solutions. So those 4 words are used interchangeably when we're talking about a quadratic. There's one other feature of the quadratic we should pay attention to before we graph, no matter what form it is in, and that is the letter A that is in front in each of these forms. So here's our letter A, and that tells us 2 things about the parabola. It determines which way the parabola opens. If that A value is positive, our parabola is going to open up. So it makes a U shape, like a bowl. If the A is negative, the parabola is going to open down. It's been reflected, so it's going to make an umbrella or a mountain. The A value also tells us about the width. And this is really the absolute value of A. We ignore the sign. And if the absolute value of A is greater than 1, then our graph is going to be narrower. It's going to be skinny. If the absolute value of A is less than 1, then our graph is going to be wider or fatter. So some examples of what this might look like. If our graph is going to be narrower, we might see 2x squared. We might see 3/2 x squared. Even though that's a fraction, it's greater than 1. We might see something like negative 7x squared. That would be a skinny graph that opens down. If A is less than 1, it might be something like 1/2 x squared. It might be something like negative 1/4 x squared. So that would be a wide graph that opens down. Or it might be 0.3 x squared. So it could also be expressed as a decimal. So let's get into some graphing. We're going to graph each of the forms. And the first form is called vertex form, because we can actually see the vertex as we look at this form. So our steps for graphing are here. First, we're going to look at the form and state what the vertex is. And then we're going to sketch in what we call that axis of symmetry, that straight line that gives us 2 mirror images. We're going to plug in 2 x values on the same side of the axis of symmetry, plot those points, and then make the mirror image across the axis of symmetry. And then we'll have enough points to establish the shape of our parabola and make that smooth curve. So as we look at our first graph, written in vertex form, what we should notice here is with the x value, we have minus h. There's a negative built into that formula. So I always remember that your ex, like your ex-boyfriend or your ex-girlfriend, is a liar. If this graph says plus 3, then our vertex is going to have a negative 3 as the x-coordinate. That's our h. And our k, our vertical or our y-coordinate, is out here. That is 5. When we know the vertex, we also know that axis of symmetry, that mirror image line, that's at x equals negative 3. So those two always go together, the vertex and the axis of symmetry. The other thing we know is that a is negative, so our graph will open down. Now, we need a couple of other points to plot. So we could go on either side of our vertex, which is at negative 3, 5. So I'm going to go ahead and plug in negative 2 and negative 1. So when we plug in negative 2, we just need to remember PEMDAS. So we are going to square the 1 and then make it negative. So our point that we could graph would be negative 2, 4. And then I'm going to plug in negative 1. And that gives us 1. So our other point is negative 1, 1. Now I'm going to plot the axis of symmetry in red. And that's that vertical line. It's not really part of our graph, but it does make a mirror image. And now I'm going to plot these 2 points, negative 2, 4, negative 1, 1. And that shows us the right side of our parabola, the right side of the curve. So now we make the mirror image. This point is 1 unit to the right of the axis of symmetry, so we'd have 1 over here, 1 unit to the left. This point is 2 to the right, so we'd have 1 over here, 2 to the left. And there is our parabola. If you're a table of values kind of person, we could graph it like this. So we always need usually 5 points to get that curve. And we always want to think of the vertex as our middle point, negative 3, 5. So I went ahead and plugged in negative 2. That gave us 4. And negative 1, that gave us 1. So 2 points that are to the left of the vertex here in the middle. So remember, vertex is a really important point there. And then we could go with 2 points to the left, negative 4 and negative 5. Negative 4 is at 4 and negative 5 is at 1. So tables of values are always helpful, but remember that axis of symmetry helps you get that graph. Now in standard form, we don't really see much right away about our parabola except for the a value. The b and the c are not actual points on the graph, but we have this formula to help us find the vertex. And what we know is that the x-coordinate of the vertex can always be found by doing the opposite of b over 2a. So we're going to look at those coefficients and we're going to do the opposite of b over 2a, and that's going to give us the x-coordinate of our vertex. Once we know the x-coordinate, we can plug that back in to find our y-coordinate, and then we know the vertex. The x-coordinate of the vertex is always the axis of symmetry, so we can plot that, and then we'll also know the y-intercept. The y-intercept where our graph crosses the x-axis is the point 0, c. So that last constant tells us the y-intercept, and then we can reflect that, find another point and reflect that, and we have enough to graph our parabola. So as we look at what we're going to graph with this example, we know a couple of things, and I'm going to write those down first. A is positive, so our graph opens up. We also know that A is greater than 1, so our graph is going to be narrow, narrower than that original parent function. So as we're working with these values, we know that A is 2, B is 4, and C is -3. And in standard form, the first thing we're going to do is find the x-coordinate of the vertex, the opposite of B over 2 times A. So the opposite of B would be -4 over 2 times the A value of 2 would give us -4 over 4. So the x-coordinate is 1. Sorry, -1. -4 over 4. Let me correct that. It is -1. Once we know the x-coordinate, we need the y-coordinate. So we're going to go back in, and we're going to plug in -1 into our function to see what we get. As the y-coordinate of our vertex. That gives us 2 times 1 minus 4 minus 3. So 2 minus 7 equals -5. So our vertex is at -1, -5. That also means our axis of symmetry is at x equals -1. Remember, those are always connected, vertex and axis of symmetry. The last thing we can know and automatically graph is our y-intercept. Our y-intercept is 0, c, so ours would be 0, -3. So let's plot what we have so far. We have the vertex at -1, -5. We have the y-intercept at 0, -3. And we also know that our axis of symmetry would come down right here through the vertex. And because that creates a mirror image, I'm going to go ahead and reflect the y-intercept on the other side of the axis of symmetry. So now I need one more point. So let's plug in, I don't know, a value of x equals 1. Let's see what happens when x equals 1. When we plug in 1, we get a value of +3. So over 1 and up 3, that's another point on my graph. And again, using the idea of symmetry, we can reflect that on the left. And then we plot those with a smooth curve. And there's our skinny parabola that opens up from standard form. So in your notes, make note of the opposite of b over 2a, which is how we find the vertex, and that the y-intercept is 0, c. The last thing we're going to graph is a parabola that is in intercept form. So P and Q, whatever is inside those two separate parentheses, that's your giveaway that it's in intercept form. P and Q are the x-intercepts. So remember, those are also your roots. Those are also your solutions. And they can also be called your zeros. Because of the symmetry of a quadratic graph, if we know the two x-intercepts, they're going to be on either side of the axis of symmetry. And that axis of symmetry would also give us the vertex. So halfway between the two intercepts would be the x-coordinate of our vertex, which is also the axis of symmetry. So when we add p and q and divide by 2, that's like what you did in geometry class. You're finding the middle. What's exactly halfway between these two roots? Once you know that x-coordinate, you plug it in. That will give you the y-coordinate of the vertex. You've got the axis of symmetry. And then we're going to find one more point and reflect it to graph our parabola. So let's look at our graph here. Let's notice our a value. There is no a there, so a equals 1. So that's positive. So our graph opens up. And it's going to be normal. It's not greater than 1. It's not less than 1. So it's going to be that curve that we're used to from our parent function. It won't be wider and it won't be skinnier. So what we do know, if we have x minus p, which we could call x minus 1, and x minus q, which we could call x plus 3, remember, because it's with your x, like your ex-boyfriend or girlfriend, it's lying. If it says x minus 1, there's a negative built in. So our x-intercepts are positive 1, 0, and negative 3, 0. So we have 2 points on our graph already, and we could go ahead and draw those in, 1, 0, and negative 3, 0. Remember, those are x-intercepts this time, not y, x-intercepts. And exactly halfway between those, we should find our axis of symmetry. So there are a couple ways you could do this. If you're more visual, we could plot these points, look at the graph, and then say, well, these are 1, 2, 3, 4 steps apart. So right here at negative 1 should be the axis of symmetry. That's exactly halfway between. The other way we could find that is to do p plus q divided by 2. We're finding the midpoint. So if we do 1 plus negative 3 and divide by 2, we get negative 1, which is the same thing we saw visually on our graph, that at negative 1, we'll have that mirror that creates the two halves of our parabola. Now we know that the vertex has to be on that line. It always matches up with the axis of symmetry. So we know the vertex starts at negative 1. That's the x value. But we have to plug that in to find our y value. So negative 1 minus 1, negative 1 plus 3 gives us negative 2 times 2, which is negative 4. So there's our vertex at negative 1, negative 4. But we need, one other point. So we want to pick something that's easy to find on our graph. So let's plug in 0 into our function. And we get negative 3 as our y value. So 0, negative 3 would be a point on our graph. We can use the property of symmetry to reflect that across the axis of symmetry. And now we have 5 good points. And we can graph our parabola. So remember that in factored form, P and Q are your x-intercepts, and halfway between those at the midpoint is your axis of symmetry and the x-coordinate of the vertex.